Recording is rolling. It is Monday, March 24th. So we're starting a new topic today, which is electricity. So I have some posters for you guys today I'm going to go through. I have some live demos in front of you. Got some electronic components here. And I got some Paul Hewitt videos. So what we're doing today, electricity, there's a new unit involved. Actually, a few new units. This whole page, you guys haven't seen most of these before. And when we get to circuits, this is really a new way of thinking about things. So when we get to electricity circuits and say that, like, how does current flow around the electricity circuit? It's going to take a few days to build up. Uh, this could also be useful for if you're a pipe engineer one day and you build a whole pipe system, you got water routing around the city, or if you're a traffic engineer and you have cars flowing around, you have to figure out like how much traffic is along each branch of road, right? That's the same type of thought process as these electric circuits. But again, this is completely new. So make sure you're paying close attention today because yeah, for the next few weeks, this is all kind of branched from today. We're setting the foundations for. All right. So let's do let's do a few posters and we might toggle back and forth between some of these. Right. So way back to last semester, just to have a little contrast here. I remember there are different ways to measure different fundamental variables, and these were the three measurements that carried us all through first semester. So mass in kilograms, distance in meters, and time in seconds. Right? And then we could have some combination of these. So for example, a force. If you push something, that could be a force, or if you lift something, take some force to lift it. That's newtons, which is kilogram meter per second squared. I remember momentum units with some combination of these, energy units with some combination of these, power, something. Right? So just over and over, all you needed was those three, right? Just all through the first semester. Okay. Now, you might remember too, there are some other things that maybe you can't measure with just those. Like, for example, moles and from chemistry, you guys remember counting in moles, right? So that's its own thing. How bright is the ceiling light? You can measure in candelas, right? What's the temperature of the room? Right? That could be in kelvins or Celsius or Fahrenheit, but none of these kilogram meter seconds. Right? But this one right here, you guys see amperes for electric current. Right? So that's going to connect us to what we're going to be doing for the next few weeks. Right, so let's get actually, I have an expanded version of this. Okay, so let's look at the expanded version. See more going on with this. Okay. Really just focus on this yellow part of the table. This green part, we'll say that for later, but for the next couple of weeks, we just care about these yellow variables here. Okay. So at the top, I have an electric charge is going to be measured in coulombs. So what does that look like, an electric charge? Right. I do have a Van de Graaff generator back there. You guys see the Van de Graaff? Now, at some point, either beginning class, end of class, or later on this week, I'll set you guys up with a lab. If you guys get a chance, you can switch that on and shock yourselves if you want, because it can build a static charge. I can do that here with this balloon. I can take this balloon, I can rub this against my hair, and then what's happening is the latex from the balloon is going to, ooh, that shocked me a little bit, is going to steal some electrons from my hair. And see if I can put this against the wall. It's going to stick to the wall. And let's try this a little bit more. Ah, there it is. Right, and that balloon will stick to the wall. Say it one more time. How'd it going? I'm just working really well today, and sometimes like, yeah, okay. So there. So balloon sticks to the wall right there. Right. All right. Or how about now you can't see it on a film, but which you can see on camera. Maybe it's this right here. So I got this aluminum foil. Got this balloon. What do you think is gonna happen when I put this foil next to this balloon? What's gonna happen? It's gonna, oh, it attracts it. You see, it attracts it, right? Now, ooh, this foil here. Okay, so it's aluminum. It's a metal. I know something about metals. I know they're useful for making wires, right? Because the electrons, it's really easy to move around inside the metal. So when I put this negative charged balloon next to this metal, there are some electrons, just a few, it only takes a few, that are repelled away, and it leaves the metal behind as more positive charge. And it's going to attract to the balloon. Is that right? Because what happens to a positive charge and a negative charge? Opposite charges do what? Attract. Aha, opposite charges attract. So I think like charges are going to repel. And see if I can possibly do that. I have here a couple of pieces of tape that I stuck together. Let's get these posters off just for a moment here. All right. So I got these two tapes stuck together. Now, if I tear them apart really fast, then the charge is not going to distribute evenly. charge up my balloon again, get that balloon ready to go right there. Come on, sit right there. Okay. If I tear these apart, let's see. Okay, so I bet one of these is positive, one's negative. Let's see if that's true. If I move them close together, if they're, does that really work? I don't think that really worked. Let me give this another shot. This is one of these demos that sometimes works really well and sometimes kind of iffy. So maybe if I tear it apart faster. All right, so I've got my tape. There's apart real fast. Zoom. Okay, let's see. If I bring them together. No, it's not really working. Let me put it next to the balloon. Well, actually, yeah, this one gets some kind of maybe. Right. Put this. Okay. Yeah, this is not working as well as it usually does. Right. But one more shot. All right, let's see if I can get this to work. Ooh. Okay, that's doing something with the balloon now. Right. If I put the balloon next to this piece of tape. Okay, yeah, it's working. You see it's repelling away? It's repelling away. It's definitely pushing away, isn't it? Ooh, look at that. Pushing the tape away. Right. So if the balloon's negatively charged, that means this tape I'm holding is how charged? Positive. So if I put this down, probably neutralized it, whatever. Right? And I bring in the other tape, which is probably sorry, what did I just say? All right, I think I got that backwards. Sorry. If they repelled, that would be negative and negative, wouldn't it? All right, sorry. Those were both negative. That's what I meant to say. Negative and negative repelled. Now, if I have negative and positive, that's going to, all right, okay, it's a little bit of attraction. It's kind of weak, but it's kind of there. And so it looks like the same charges, like negative, negative, are going to repel, and the same and opposite charges, positive and negative, are going to attract. Okay, so there's a good starting point. Okay, get this out of the way. Sticky tape. Okay. All right, so there's your point charge. Just electric charge can be measured in coulombs. And let's see what that looks like. So a single charge is all you need to create an electric field. That's what this E is, electric field. Okay. And what do we got here? So how charge is in coulombs? So this Q could be the charge in coulombs. Okay. This K is an electrostatic constant. Actually, I got that on the next page, so I'll show you guys right here. Electrostatic constant is what K is. Okay. And this D is how far you are away. Okay, so if I back up and get further and further away from this balloon, I feel less and less force from the balloon, right? So, or less electric field, I should say, right? And that tapers off 1 over the distance squared. Now, if you have 2 interacting charges, which is what this next one is, now there could be an interacting force. And look, I got opposite charges here. If I have positive and negative, are those going to do what again? Attract or repel? Attract, right? That's why I got this attraction going on, right? And hey, look at that. This looks a lot like universal gravitation, doesn't it? You guys remember like the Earth pulling on the moon? It went G-M-M over R squared, isn't that? Okay. So this has, instead of 2 masses, it's got 2 charges that could be quantified in coulombs. Okay. It's got this electrostatic constant instead of the gravitational constant. And in the distance, well, it's still a distance. It tapers off 1 over the distance squared. Okay, same way. Okay. So you guys get this. Look at this electrostatic constant, 10 to the 9 and in a bunch of units. Versus, you guys remember gravitational constant was like 10 to the negative 11, right? So guys, which of these constants for gravity or for electricity is way, way bigger than the other one? This one right here. Isn't this like 20 orders of magnitude bigger, right? 10 to the 9 compared to 10 to the negative 11? Yeah. So this is considered to be a much stronger force than gravity, right? And you can see that right here. So if I drop this object, Earth's gravity holds it down. But as soon as it hits the table surface, guys, this table surface, that's all electrostatic charges. It's all just made of atoms. You got electrons pushing against electrons, and that's what's holding it up. That's way stronger than Earth's gravity pulling it down, so the table stops the object. Like that. All right. Now, that's all this right here. So you guys get that one? Right. Now, next row. Ooh, it's electric current. Now I'm going to use I to represent electric current. If you see I for the next few weeks, that's electric current. And that's going to be measured in amps, amperes or amps. Right? And what is 1 amp? That's 1 coulomb per second. Right? So really going back to my base SI units, backtrack a little bit here. I was saying amperes could be for electric current. there are alternate versions of this that have coulombs. So you have to either start with amps or coulombs, and most textbooks start with amps. That's why I just put amps on here, right? But you can have one or the other and then derive the other. Okay, so 1 amp is 1 coulomb per second. So that's a rate flow of that charge. If you get that charge flowing at some rate, right, coulombs per second, that could be amps. You guys got that? Okay. All right. Now, why would electricity flow at all? It only flows if there's some impetus to flow. Like, why does a ball roll downhill? Well, there's got to be a gravity field and a height difference. Right? So same thing with electricity. Why does current flow? Is if there's a potential difference, also called voltage. Now, what is 1 volt? It's energy per charge. Okay? So joules per coulomb in the metric system. I have some batteries here. Every battery has some voltage in it. Okay? Does anybody happen to know how many volts is a AA battery? How many volts is a AA battery? See, it says here if it comes into focus. Come on, focus. No, that just looks blurry. Right. Anyway, it said, oh, can you guys read that? Aha, 1.5 volts. Right. All AA batteries are 1.5 volts. That's also true for like C cells and D cells. They're all 1.5 volts. Okay. It has to do with the chemistry inside the battery. Okay. Actually, I have a poster for that. Let me dig that up real fast before I miss it. Where's my battery? Here's my battery. Okay. Here's one way you can make a battery. Okay. It's just different chemicals. So you need a cathode and an anode. For example, manganese dioxide and zinc. Okay. And maybe an electrolyte like potassium hydroxide. Okay. And then that battery could just sit on the shelf for years. Right? And then those chemicals are just sitting there. Right? But if you get this negative lead connected, now you have a route for the electricity to flow. Right? Maybe if you get a closed circuit, right? And that would be some kind of current flowing. Okay. Where is it here? Right. Oh, so back to batteries. I've also got this boxy battery. Now remember this AA was 1.5 volts. Does anybody know how many volts is this big old boxy battery? It's more than that. Not quite. Close. 9. Again, this camera. Yeah. You guys say 9 volts. It's a 9 volt. If you ever hear a 9 volt battery, there it is. 9 volts. Think this right here. It's your 9 volt. And that's like 6 times as much as this little guy right here. Okay? You'll see some different batteries today. So here's 1.5 volts. Here's 9 volts. Get an idea. I also have some Christmas lights. Later on this week, I'll give you guys some Christmas lights. I'll also give you guys some of these little breadboards. We'll look at this later too. Okay? But let's try the Christmas lights just for now. What if I connect the leads of the Christmas light across this 9 volts? What's going to happen? Ooh, look, it lights up real bright. You see it light up real bright? Okay. So here's my voltage source. That's like how many volts is the battery. So I got 9 volts here. Okay. Each one of these lights is one of these right here. It's called a resistor. So it provides some resistance. And resistance we're going to quantify in ohms. And 1 ohm, that's Greek letter omega for ohm, breaks down into volts divided by amps. It's like the same thing. Okay. Right. So everybody good so far? So suppose I have 9 volts here and I have 1 ohm of resistance. That's going to induce some current to flow. Okay, now how much current flows? Well, I have a very short equation for you guys here pretty soon. You guys, okay? You guys get that? Okay. Hey, how about this? Now this will show up way later in class today, but actually I have 2 connected one after another. It's called in series. That's the term for it. It's called in series, one after another. Okay. What if I connect like this? How bright do you think it's going to be compared to before? Yeah, each individual bulb is not as bright. Let me show you guys. Here's 1 bulb by itself. Ooh, that's really bright. Here's 2 bulbs in series. Each bulb is dimmer than before. What if you had like 5 bulbs? Do you think each bulb would barely be visible? Probably, if they were all in series. Now it's different from, what if I connect them like this, which is different? You guys see how both leads are got left to left and right to right? Okay. Now it's still 2 bulbs, but now it's called in parallel. You also see that close to the end of class today. Whoa, we're back to crazy bright. Each individual bulb is crazy bright. Whoa, look at that. Is that? Okay, now hold on to that idea because you'll see all those ideas later. You guys good so far? Okay. In fact, how bright the bulb is actually like this concept right here. Power measured in watts, which is something that you guys know from last semester. You guys remember that's a rate of energy transfer, like joules per second? Now if you buy a bulb from the store, it's usually quantified in watts. Like, oh, this is a 20-watt bulb, something like that. But really that corresponds to whatever outlet it's put in, if you're on the American electric grid or a flashlight or whatever, right? So really the bulb itself is probably at some amount of resistance, but they could say, well, in an American light socket, it would probably be like so many watts of power. Okay, please go. Right. And then these green ones we'll save for in the future. We'll just focus on this yellow part today. All right, you guys good so far? What you guys can see. All right, so you guys saw an electric field with an electrostatic charge. If you have two interacting charges, there could be some kind of force involved. And right, and we're gonna work up to build some basic circuits today. So what are some things you can put on a circuit? Okay. Here's the main ones I care about is battery and resistor. That's the main ones you care about. Okay. So if you see two parallel lines, one longer than the other, that represents a battery or a voltage source, but usually a battery. Okay. And the long lead represents the positive side. Okay. So could have a battery, just like that, battery. Okay. Resistor is this jaggedy looking line. That could be like one of these Christmas lights right here. Bam, there's your resistance right there. Okay. In fact, that could be a basic flashlight right there. Now you could also have these other things on here. I think you'll see a switch today, but these are the ones that capacitor inductor we'll save for the future, so not really today. Okay. All right. This battery, you guys saw the battery. You guys know what that battery looks like. Got some chemistry going on in there. Flashlight schematic. So here's your voltage source for the electricity to flow. Right, here's the resistor. Now you do want some resistance on your circuit because what would happen if I just took a bare paper clip, or how about this coin right here? Or I got a coin, I got a paper clip. Now I'm not really going to do this, but what if I took a paper clip and I just put it right across these two leads and touch the two leads together? What would happen? Yeah, the paper clip would get extremely hot. Yeah, really hot, really fast, and the energy of the battery would drain really fast. Right? There's a term for that. You do not want this to happen. It's called a what kind of circuit? Starts with an SH. Yeah, it would be closed. It'd be a short circuit. Short circuit. Aha. Right. You guys ever hopefully not drop your phone in a tub of water? Right. Shorts it out. Because it's creating passive electricity flow where it's not supposed to flow. Right. Shorts it out. Right. So you do want a resistor to be in your circuit. Right. And this schematic could correspond to this flashlight. Look at that. I got my battery right here. I got my light bulb resistor right here. I even got a little switch right here. Right. How about this? If the switch is open, if it's open, so the wires aren't touching, is the electricity going to flow? Yes or no? No. So the light doesn't turn on. It's off. What if I close the circuit? Close the circuit. Now can the electricity flow? Aha, I can. Does the bulb turn on? Yeah. So closed circuit, the bulb's on. Okay. Okay. Now, how much electricity flows? Here, I'll show you guys this one. It's called Ohm's law. So the more voltage, the more current flows. Like if you double the voltage, guys, if you double the voltage, is that going to double the current? Yep. What if you double the resistance? If you double the resistance, what does that do to the current? Get half as much. Right. So you guys see that relationship? A direct relationship between V and I, an inverse relationship between R and I, where I is current. Right? See if you guys follow this. What is voltage measured in? Volts. Right? It's also called potential difference, or some textbooks throw a little delta in front of it, like delta V, potential difference. Some textbooks use an epsilon. So if you ever see an epsilon, right? Did you guys follow what is resistance measured in? There, go back for that one. Resistance, we'll just call it ohms. Okay, ohms. Greek letter omega for ohms. So potential difference. Oh, there's my epsilon right there. Okay. I usually just use V. V for voltage measured in volts. Guys, that's kind of a weird thing too. I think this is the only time in this entire class I ever do this, where I treat the variable and the unit as the same letter. Capital V, capital V. I think it's the only time I ever do that. Okay. Some textbooks don't. Okay. And then some current's going to flow. Guys, what is current measured in again? Amperes, or you can just say amps. Amperes or amps. Okay, everybody good with that? Right, there's Ohm's law right there. Ties it all together. Okay. All right, flashlight schematic. Got that. Okay. Now, when I first learned all this stuff myself, because I learned this all in high school, but this didn't click for a couple of weeks. Because like volts, amps, I don't know, maybe it's kind of abstract, or at least to me. It's like I can't really see any of this happening. Right? Until I learned this analogy, and then it all clicked. This is a really good analogy anyway. Electricity flowing through a wire is kind of like water flowing through a pipe. actually, if you are a pipe engineer and you're designing a pipe system, or later on you'll hear a traffic analogy, you have a traffic flowing around the city. You can actually use these exact same concepts in the same math and figure out how to make things flow through different types of systems, right? So we hear voltage, think of it like pressure. This battery, think of it like a pump trying to push electricity through the circuit. Now, you do want a resistor in your circuit, and think of it being like a crimp in the pipe. It's going to slow things down. Again, if you did not have any resistance, you would short out the circuit. You would drain your battery really fast. That would be not good. Right? Unless you wanted to start a fire, you could start a campfire with this. Okay? All you have to do is put this paper clip right here, put on some leaves, and start a fire that way. And then the current that flows, measured in amps, think of that being analogous to a flow rate, like gallons per minute or cubic meters per second. Like how fast is the water flowing through, volume per time. Okay? Also, when we get to Joule's law, and there's some other laws we won't quite get to today, this analogy works perfectly well to bring back to like a Newtonian world, back to like last semester. So, over two. You guys good with that analogy? Oh, good. Great. What's I got here? So later this week, I'll give you guys a bunch of things to do some labs. You guys have a breadboard. No, you guys see this breadboard right here? Okay. Now, if you flip over the breadboard on the backside, there's some kind of sticker here. And I'm not going to take this off because it'd be all sticky. But if I did, it would look like this. And you have to know this because you have to know how are the metal strips wired so that you can connect all these little components. Okay? Got some LEDs here. I got another resistor right here. Okay. What's this going to look like? So do you guys see how I have 5 holes where I can pop things in right here, plug things in? There's a metal strip behind these 5 right here. And then over here, now there's a gap. And then over here, there's another 5 right here. And then there are a couple of rails or buses, sometimes they're called rails or buses, that run along the entire length of the breadboard right here. Okay, you guys see all that? Okay. Now, if I plugged in this component like from here to here, right, I'm giving you guys a counter example. I would never want to do that because that connects this metal strip to this metal strip. That will never, ever, ever light up. Okay? But if I connect it here to here, you see it's like bridging the gap. It's like bridging from right here to right here. You see that's what I just did? I'm bridging that gap. Same thing for this middle one. This middle one is bridging the gap from this metal strip to this metal strip. And this resistor on the left side is bridging from this bus to this metal strip. You see that? Right? Okay. Now that I can send electricity across. I'm going to do that with, well, how about some wall electricity? Now, you guys know what the batteries are. I got 1.5 volts, I got 9 volts, I got all that. That's all fine and good. Okay. This is connected to the wall. Does anybody know how many volts are in the wall socket? More. 120. Aha, 120. Right. Also, it's alternating current, not direct current. I'll talk about that, not today, but in the future. So it's a different kind of electricity. Do I want to do this? Do I want to go, oh, I'm just going to go jamming the paper clip in the wall socket? Guys, is everybody awake right now? Guys, everybody look up here? Guys, this is really important so you don't die by Friday. Do you want to go? Yeah, or maybe make a hospital visit, one of there. Do you want to go jamming paper clips into the wall socket? The answer is no, because you'll feel 120 volts of alternating current all at once. Not so good. But what if I take a cell phone charger and I plug this in? And this converts 120 volts AC down to just 5 volts direct current. Now, I got a couple of leads here. Let me find my leads. 5 volts direct current. Is it safe to touch these leads right here? Is that safe? Can I touch these? Yeah, 5 volts direct current. That's more like in line with these batteries. That's not so bad. Okay. This is 9 volts direct current. It's probably, I can touch that. Okay. Although I've never tried this, but I've been told if you like lick the battery, you can like feel a little tingle on your tongue or something. I don't know. But let's see. Kind of light this up. What's this gonna look like? Oh, look at that. Here, make a better connection. Do you guys see the bulbs light up? You guys see that? I got a red bulb and a green bulb. You guys see that? Because the current is forced to flow through this whole circuit. You see that? Yeah. Now, here's an extra little detail, but this might be helpful later this week. If I switch the leads, guys, notice I switched the red and the black. Is that? The bulbs will not actually light up anymore. Look at that. See how the bulbs don't light up? Right. Now, this is specific to LEDs. These little LED lights, they're polarized, so they only work one way. So let's go back to the original way, and now the electricity flows through again. Right, you guys see that? The LEDs light up? Okay. Let's try my Christmas lights. Try my Christmas lights right here. Ooh, look at that Christmas lights light up. You guys see that? All right. All right. So breadboards. You guys see those later this week. Now, I got a new tool for you guys. I got a multimeter. So let's go back. Last semester, you guys used these tools to measure these variables with these units. And look at the very bottom of this list. Voltmeter and ammeter to measure voltage and current in it. So voltage in volts or potential difference in volts, and then current in amps. You guys see that? Okay. So this is a new tool, and you measure these things in different ways. You guys remember voltage is like you're measuring a pressure. So you have to connect the voltmeter aspect, what's called in parallel. I'll show you guys this real soon, right? In parallel, and then you're getting a potential difference that way. Okay? But when you switch over to the ammeter aspect of the multimeter to measure the electric current, you guys see how I have to break open the circuit and I have to force the current to flow through the ammeter? Is that which is different than this? These are different, right? Voltage you measure in parallel, current you measure in series. So I have a multimeter right here, right? Now I'll give you guys a quick rundown right today, but later on this week, you guys are gonna have to know how to work this. All right, you guys ready? Everybody paying attention? All right, everybody looking up here, up here. So later this week, when you guys get the lab, you'll know what to do. Okay. Now I have 3 places to plug things in. 3 places. You guys see those 3? Okay. But I only have 2 leads. So here's what I'll do. I'm gonna take the black lead. I'm gonna plug it into the one that says COM. That is always going to be there. Okay, you guys got that right in the middle? Okay. Now the red lead, it depends what I'm trying to measure. You guys see this one says volts and ohms and something, right? In temperature, something like that. And this one over here says something about amps. Okay. So for the side, I'm going to plug this in the one that says volts to measure the voltage. You guys that? Okay. But I also need to move this toggle switch. And the top left are different volts direct current. Now if it's a flat line, it's direct current. If it's a wavy line, that's alternating current. We're not going to do anything with alternating, but we're going to do direct current. Now these in the top left, they're all for volts on the battery. All it does is it moves the decimal point. Guys, watch this decimal point. You guys see that decimal point floating around? You guys see that? Right? But it's right now it's 0 volts. 0 volts. But if I take these 2 leads and I put them on this 9-volt battery, what do you guys think this 9-volt battery is going to read? It's going to be 9 volts. Let's see if it is. Ooh, negative 8.9. Ooh, hey, how could it be not negative? What can I change to make it positive? Switch the leads. Maybe I should put this red lead on the positive and the black on the negative. Ah, now it's positive. It's positive 9. Positive 9. You see 9 volts? That's a 9-volt battery right there. How about, where's my cell phone charger? I said the cell phone charger was 5 volts, right? Let's see how true that is. I haven't actually done this today. Let's see if this is 5 volts. Showing like 3.2. All right, that's pretty close. Right. So voltage, you can get a little leeway. If it's plus or minus a couple of volts, that's okay. Right. How about what if I want to measure current? Now, to measure current, I have to make some changes. So everybody still watching? Right. So I'm going to leave the black and the COM. I'm going to take the red lead out. Pop it in the other one that says amps. I also need to change this toggle switch. I'm going to switch over to the one, it says something about milliamps or something. Right, it's not quite the orange one. It's right before that. It says like milliamps. So I'm going to leave it on that one. Right. Right. And also, I can't connect it in parallel across something like that anymore. Right. I have to connect it. I have to open a circuit and force the electricity to flow through. So how can I do that? I'm doing my best here. How about what if I connect my Christmas lights? One lead right there. Now, no, oh, look, they're not on. Now if I connect them this way, now they're on. Right. Now they're off. Right. Right. But what if I connect this lead right here and this lead right here? I know I got a lot going on in the same frame. Try to get this all on the same frame right here. That's that here. Do this. Connect this way, this way, this way. Aha! You guys see 5.4 amps? You guys see that? 5.3 amps? You guys see that? Okay, so 5.3 amps we're going to call it. Okay. So switch that off. Okay, so switch that off and save the battery for next class and put that away. Okay. Okay, so you guys did with the multimeter so far? I know that was a real fast rundown. But later this week you guys get to use that, and I'll help you guys out with that too. Right. All right, good so far, good so far. All right, now I do have some more posters, but I've been saving Paul Hewitt for you guys. So let's backtrack a little bit and see Paul Hewitt's take on some of these concepts.
This was called the Van de Graaff generator. It's named after a person by the name of Robert J. All right, we be learning this stuff. All right. Now, what we're going to do here, it's talked about in the textbook. It turns out this belt is going to carry charges from little lightning points here, deposit them up in here, and we're going to build up an enormous charge on the top. Let me show you what I mean. Notice I am, notice that I am keeping, this closer to the dome than my head. Guess why? I don't want to put my head closer than this, all right? Well, let me show you that that does charge. Let's try this again.
Ooh, I want you guys to predict before you see this. So he has a stack of pie plates. Now they're all metal. They're all individual. Maybe there's like a stack of like 10 pie plates. Okay? What's going to happen when he puts them on that positively charged dome? Huh. See, they're all metal. Do you think they'll probably all adopt that same charge? If you've got a bunch of individually charged pie plates and they're all positive, 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 what are they going to do? Aha! Aha!
And so the flow of current was proportional to voltage difference. Not how much voltage, but how much voltage in one place compared to the other. Think of voltage as a pressure. Huh? So it's proportional to voltage difference. Proportional to. So the more voltage difference, the more. Hey, imagine I have a pipe right here filled with water. Okay, see that water filled pipe? I have a piston over here and I have a piston here. And I push with a certain pressure, maybe 5 units. I push with the same pressure here, 5 units. Which way does the water flow? But instead of water ain't gonna flow at all. I say, yeah, I got under pressure. And you say, yeah, but there's no pressure difference. How about I push here with 5? And I push over here with 3. What does the water do, gang? What does the water do? The water flows, okay? And similarly, if you take a piece of wire and you put a pressure difference across the wire, and I can do that here. Here's a lamp, okay? This is a 12-volt battery. One end is 12 volts higher than the other. If I touch here and touch here, no light. If I touch here and touch here, no light. There's 12 volts, 12 volts. Why no light? Check your neighbor, why no light? Let's try the other side. No light, there's still no light. Why, how come? But I got 0 volts over here. Oh, over here I got 12 volts. There's no difference. You gotta have a difference. Look at how I go like this. A, ought to be, huh? What's the voltage difference across the lamp now? 12. So if you got a voltage difference, you get a current. It kind of makes sense. This is not counterintuitive. The more voltage difference you have, the more current you're going to have through a conductor. And this is a conductor. It's a piece of wire made out of copper where electrons can flow all through there, gang. So I have a conducting path with a voltage difference. No voltage difference, no current at all. Voltage difference for a current. Make sense? When you touch a wire, a lot of times people touch a wire and they can't let go. You know why they can't let go? People, oh, they attracted to the electric. No, he ain't attracted. Contraction. Remember the biology experiment you do, the frog's legs, the frog leg like that, and you come over and you touch it like that. The frog is dead, honey, and it's still going like that. It turns out it's an electrical. Can you guys do that? Try it. I hope you can. Do you know what you guys are doing? You are sending electrical impulses down your hand. It's electrical impulses to do that, and it contracts. So what happened when you touch the wire? It's not that you attract, it's that your fingers contract. So he told us that electrician types, always if they're fooling around, they touch like this. You touch like contract, you can pull away, see? You're okay. But you don't want to go like that. You know what I'm saying? Practical stuff. Hey, why is it that you see birds on high tension wires, bare wires? And you see the bird come down and he grab on a foot and stand on one foot and he's on the wire. And the bird doesn't get fried. The bird's okay. Now what happened? The bird reached down and put the other foot on the same wire. What happened to the bird then? Begin with N and with nothing. Try it. Nothing. He said, bird's okay. Look, hey man, the bird's 100,000 volts. Is the bird all right? The bird is all right. Because you get 100. What's the voltage difference across the bird? Zilch.
Now, what if the bird puts his left foot on a 100,000 volt wire and his right foot on a nearby tree branch? Now what? Now a current does flow through the bird, right? So now there actually is a difference of 100,000 volts.
Zilch.
Chicken dinner.
This relationship, current proportional to voltage difference, becomes an exact equation when I include the idea of resistance. If you have a humongous resistance, even for a big voltage difference, the current will be very small. So how much current flows through things has to do with two ideas, gang. What's the voltage difference across the ends of the conductor? And what's the resistance that that conductor offers to a current flow to begin with? And that usually has to do with the geometry and the material of the conductor. Like a great big fat piece of copper has less resistance than a little skinny piece of copper. Just like a great big humongous pipe will have less resistance to the flow of water than a little skinny pipe, yeah? And how about a lamp like this? This copper right here, it's relatively thick, but it's very, very thin in there where the filament is. Guess where most of the resistance is across these two leads? Begins with FIL. Filament. In that filament is most of the resistance. And guess where most of the energy is dissipated going from here to here when I touch it across the battery? Right in the filament. In fact, the filament reacts so bad, it turns white hot with heat. Look at that. It's glowing. And there's your lamp. Isn't that nice? So we measure current in amperes, amps, okay? And we measure voltage in volts. And we measure resistance in all together now. Ohm. Okay, there's an ohm, yeah, that's ohms. In fact, ohms are written like this. Greek letter omega, ohm. Voltage is written like this, V, and current is N. Amps, the unit is amps, and oftentimes we call current I. So we could say I equals V over R. And it's the old song and dance, gang, that if you know two of these things, you know the other. Like, for example, let's suppose I tell you the resistance of this little lamp is 1 ohm. And I put it across this 12-volt battery. There are people in this room besides Lee who can tell me how much current is flowing through the battery. And
Right, so if you guys follow what we just said, so okay, so this is a setup. Here's this car battery down here, which is 12 volts. Okay. Now he only has one resistor, not all three. He only has one. Okay. Okay, this one. This one is the one I want. Let's do this one. Okay. Okay. So he's got a 12-volt car battery. Actually, he has it like this, but whatever. Yeah, you get the idea. Okay. He's got a 1 ohm resistance. Because what's the current flowing through? Yeah, 12 amps. Aha. Right.
And there are people that can't. Check to see if you're sitting next to someone who can. 1 ohm resistance, 12 volts across the battery. What's the answer again? 12. And that's 12 amps. That's Ohm's law. I'm going to hook this up like that. And lo and behold, it lights.
All right, here, guys, a little bit forewarning on this one. This might be the longest of these that I show you guys all over the year. It's like 5 or 6 minutes long. I'm going to pause a few points, but pay real close attention here because he's going to go through a real complete explanation of volts and amps. He's going to wire up different resistors different ways. There's this way called series, there's a way called parallel, and it's pretty complete explanation of a lot of stuff you're going to be doing for the next couple weeks.
What's the voltage across the lamp, gang? 12. What's the voltage across the lamp now? 12. What's the voltage across the lamp now? 12. In fact, you know what I could do? I could keep this battery in this room, and I could take these two leads and I could bring them to the other side of campus. And over on the other side of campus, I could go like this, and I'd say, what's the voltage across the leads, gang? And what would you guys say? 12, and it would light up over there. In fact, what do you think a wire is? A wire is just two leads that come from some power source somewhere else. But you got one of these things cut off. You hit a switch, boom, you connect it, and you're on. Just like this. Turn the switch off, boom. Turn the switch on, boom. There's little clever ways to do that. But I've got 12 volts across that lamp no matter where I put it. Okay? Let's suppose I go like this guy. Let's suppose I put another lamp in here. I'll put another lamp in series. Series. I'm using a word game, series. Huh? There's one right after the other. I should have asked you before I did it. Will a lamp glow brighter or less bright? And you guys would have said anyway, less bright. And I said, what's the voltage across the two lamps? And you guys would have said, what's the voltage across one lamp? And you guys would say, yeah, feels good, feels good.
Now what he just did, he started getting to a certain way to think about this. It's usually a little bit different way than I explain it. So I usually explain things from a macro point of view, like from the battery point of view, and he'll get like from a micro point of view. He'll do bulb for bulb. So I just want you guys to see that, be aware of that, so you can see, okay, there's a little bit different ways to think about this. Okay, so he said from lead to lead, there's a total of 12 volts because there's 12 volts from the battery. Okay, now he just said if you have these two bulbs in series, so sequentially one after another, the voltage steps down a little bit at a time. Kind of analogous to, I'll give you guys a cliff analogy with waterfalls, like a waterfall analogy later this week. It's kind of like if you have a big cliff, but it steps down twice. So I have like if there's a 10-meter tall, or let's go 12, a 12-meter tall cliff. You have a 6-meter drop here, followed by another 6-meter drop here, where the height of the cliff is sort of analogous to the voltage, right? Because the taller the cliff, the more the pressure, the more the voltage, right? Something like that, right? So the voltage steps down a little bit at a time, a little bit at a time. Now, you can almost see Ohm's law behind him. You see I equals V over R, right? So let's follow this. Here, how this place.
6. 6 and 6 is what? 12, that's right too. If you take the 6 volts across this 1 ohm, what's the current in there? But we got to go through that again. If I get 6 volts across there and the resistance of 1 ohm, 6 amps. 6 amps here. How many amperes over here? 6. In fact, in this series, how many amps right through this little point right here? How many amperes through a point right here? 6. And how many amperes flew through the battery? 6. 6. 6. 6. 6. 6. All the way along. How many amperes up here? None. This is not part of the circuit. My circuit's right through there. See what I'm saying?
All right, so that whole thing, like 6 amps, 6 amps, 6 amps, all the way through. That's current. Remember, I was saying current is sort of analogous to flow rate, right? Like you have some crazy pipe system, but it's the same gallons per minute everywhere, isn't it? Okay. Or later on, you'll see a traffic analogy. He's about to break out a traffic analogy. If you have like cars going around, if it's 6 cars on a one-way street, it's the same 6 cars everywhere. Right, so that doesn't change. Right now, the voltage can change, or they might have different resistors or different numbers of stoplights, the whole thing. But the current's the same everywhere on that one street. Right now, he's getting to resistors in series, which looks like this, right? Resistors in series. So, what I'm claiming here is that the total resistance of resistors in series, you very simply add the resistances. So if it's 1 ohm and 1 ohm and 1 ohm, guys, that would be how many total ohms of resistance here? 3, right? 1, 1, 1, 1, 3. Right? Now, actually, I paused the video where he only had 2 on there, so it was like 1 and 1 could make 2 ohms. Is that okay? Right. Right. And then now he stepped you guys through from a micro point of view. He said, well, if this is 1 ohm of resistance, and I got a 12-volt battery, so that drops 6 volts and then another 6 volts, and then circles back around to the battery. Right? I could go back to Ohm's law. I could say a 6-volt drop across each individual bulb on 1 ohm, which is each individual bulb. 6 divided by 1 gives you 6 amps of current. Right? What I'll usually do is go from a macro point of view. I'll say, well, guys, if this is 1 ohm and this is 1 ohm, then what's the total resistance of that circuit? 2 ohms, right? And then I would take that and I would go back to Ohm's law and say, well, if you have a 12-volt battery acting on 2 ohms, that gives you how much total current? 6 amps. And then since it's all a one-way street, it has to be 6 amps everywhere. Is that right? Which is a little bit different approach, but of course it gets you to the same answer. Yes, yeah.
The current flowing through the circuit, and the circuit now has twice as much resistance as before. If it quite get twice as much resistance, what's the current? Half as much. Do you see? Ohm's law kind of says it all. Ain't that neat? All right, now here's what I'm going to do, and everyone's going to get this right. I'm going to hook another lamp in series, and I'm going to connect it up, and you're going to tell me brighter or dimmer. Is there anyone says brighter? No, nobody say brighter. And what do we get? It sure is dimmer. Let me ask you guys a question. What's the voltage across the whole system? 12. Okay.
Actually, let's knock out all those questions before you ask them, and then I'll go back and play the video for review. Right. So we got 12 volts here, right? 12 volts. Okay. I got 1 ohm, 1 ohm, 1 ohm. Guys, what's the total resistance? 3 ohms, right? Yes, it's right here. 1 and 1 and 1 is 3. Okay. So 3 ohms resistance. Now, if you have 12 volts acting on 3 ohms total resistance, what's the total current leaving the battery? 4 amps. Want to be 4 amps? Okay. I'm walking out through a macro point of view, like I usually do. Okay. So there's 4 amps leave this battery, and the 4 amps go around the battery. So since it's only one-way street, like this doesn't branch off to multiple streets. Like we'll do that in a minute. We're going to branch off different streets, but we're not ready for that yet. Okay. Yeah, guys think it's the same 4 amps everywhere? Same 4 amps of current? Okay. Now let's go back to his explanation. He'll take you through a micro point of view to get to the same answer.
How much resistance we get now compared to before? 3. 3 times the resistance. How much is the current now compared to with a 1? 1/3. Ain't that neat? So now you got 1/3 of an amp.
You might say 1/3 as much. 1/3 of 12 would be 4 amps. So you guys know it's 4 amps, right? 4 amps.
Huh? What's the voltage across one of these things? 1/3 of 12. 4. Okay. And 4. 1 ohm. Oh, do I have it right? Did I make a mistake? Did I make a mistake, gang? I never make mistakes. But we have 4 volts across here. Okay. 1 ohm. So we have 4 amps. What's going through here? 4. 4. Before it was 6, and first of all, it was 12. So the current's getting less and less because the resistance getting more and more. This is a series circuit. I'm going to make a little change, gang. Look how come it's bright. How about I take a lamp now and I put it not in series, but in parallel, like the rungs of a ladder, parallel. I'm going to hook this. What's going to happen to the brightness of that lamp when I connect this?
Ooh, what do you guys think?
How many say nothing? My people, that's right. Because let me ask you a question. What's the voltage across this lamp? 12. What's the voltage across this lamp? What's the resistance of this? So what's the current through this? 12. 12. What's the voltage across this lamp? 12. What's the current through there? 12. 12 divided by 1, get it? 12. 12 amps, 12 amps, 12 amps. I mean, amps, volts, I get mixed up again. Voltage is the pressure supplied by the battery, 12. There's 12 right through across from these 2 prongs, yeah? And I pick up the 12, 12, 12. The battery gonna wear down fast now, gang, because I got a lot of amps flowing. If there's 12 amps flowing through here, how many are flowing right through here? 12. It's like automobiles driving from a garage down here. And some of those automobiles go through here and come back. Some go through here and back. Some go through here and back. If 12 go through there and you put a little checkpoint right here, how many are going through here? 12. Okay. How many through here? 12. How many through here? How many through here? What is it? It's 24. Guess you get the 12 from here and you get the 12 coming down this street. How many through here? 24. How many through here? You guys are on 12. How many through here? 36. How many through the battery? Who's getting tired? The battery. The battery. More energy going out now, more power going out. You get it?
Okay. So again, he walked you through a micro point of view building up this whole circuit. Said from this lead to this lead, there's 12 volts different. So it's a 12 volt drop across each one of these. If I did a waterfall analogy, this would be like 3 side-by-side waterfalls. You'll eventually see that. I have a poster for it. You may see it already. Did I tell you guys it's the blue? No, okay, yeah, all right. The blue banners for your thumbnail notes, right? That I gave you guys back a few months ago. Yeah, so it's like 3 side-by-side waterfalls, and they all have the same height drop because in this case they all have the same voltage drop across them, right? Or if you like the traffic analogy, it's like a bunch of cars leave this garage. They're gonna drive around town back to the garage, but they can split three different ways. Ooh, look at that. And some go down the street, some to the street, some to the street. So they split 12 cars, 12 cars, 12 cars. That's 12 amps, 12 amps, 12 amps. And they all come back together and make 36 cars. That's 36 amps. So the battery is draining at 36 amps, right? 36 coulombs per second, right? Now, again, that's a micro approach. I want to show you guys the macro approach. And the macro approach is to say that every time, and that's what this poster is, every time you add on another resistor in parallel, that's not series. There's resistors in series. There's resistors in parallel, like rungs of a ladder, that changes the total resistance. How? Like here, like if this was just suppose each one's 1 ohm. Let's stick to his numbers, right? If that's 1 ohm right there, right? Or this is like one traffic light, and the cars drive around. There's only one traffic light. And now, now the town's going to open up a new street. And okay, that's another street with a new traffic light. That's more traffic lights, isn't it? But does that make it easier or more difficult to drive around town? Easier, because now there's more paths to follow. And now we open up a new street. Right? In fact, if you open up like 1 million streets, now it'd be really easy to get around town, because like you can drive out, you can just pick, oh, well, there's no cars going around that lane. You just right. But if you have only like one traffic light, it's like, okay, well, all the cars going to be forced through that one. Right? But now you open up new lanes, but they're all in parallel. You see how the current's going to split? The current splits, doesn't it? Right? Right? But let's go back to the macro approach. Right. Now, tomorrow, I think I'll get more into this, but for now, just take this as an equation that works. Right? And I'll show you guys more why tomorrow. Right? Is the total resistance from the point of view of the battery? It's like as if there's a single resistor. Right? The more resistors you add on in parallel, it actually gets less and less and less. And it works out the you add the reciprocals and then take the reciprocal of that. So let's do it that way. Guys, what is 1/1 plus 1/1 plus 1/1? Is that 1 plus 1 plus 1? Which gives you what? 3. Okay. And then I still need one more reciprocal of that to get the total resistance. So what is 1/3? Like a third, right? Okay. That'd be a third of an ohm, because we're talking about resistance. So this 1 ohm, 1 ohm, 1 ohm in parallel, this battery down here feels like it's pushing against a third of an ohm collectively. It's as if there's a single 1/3 ohm resistor. Okay, that's it. Right. Now let's take that. There's also a product over sum, but you can only do that 2 at a time. So we'll do that more tomorrow. Right. Now let's take that back to Ohm's law, because you guys know it's a 12-volt battery, right? 12-volt battery. Right. I have a third of an ohm total resistance. Guess what is 12 divided by a third? 36. Aha! It's the same thing as 12 times 3, isn't it? Right. So that's 36 amps leave the battery. Right. Then what I would do is I say, I know that 36 amps leave the battery. The traffic's going to split 3 ways. In fact, if they're all the same resistance, it's going to split evenly. Right? We'll get more into Kirchhoff's rules later, but we're building up to that. Right? And so if 36 amps split evenly, how many amps is it across each individual resistor? 12. It's like 12, 12, and 12. Right? It's like if you have 36 cars leave this garage, and then 12 cars split this way, 12 this way, and 12 this way, and then they all come together, and then 36 cars drive back to the garage. You get that too? Right? So traffic analogy, flow rate, think current in amps. Right? If you like pressure, that's more like a pump, like voltage is like pressure. Right? Okay. All right, and then connect it all with Ohm's law. All right, so you guys good with that? Okay. And yeah, forget if I mentioned this, but I think I mentioned this at the beginning of class. I might be wrong about that. You guys remember these thumbnail notes I gave you guys? It's all the blue banners, right? Which is the ones hanging around my room right now. So if you want to hold on to those. All right. Well, I think that is a good pause point today.